Now, one thing I want to point out is we've derived this entropy balance here for a closed system overall process. We've derived it for a single heat interaction. So there's heat flowing into the system. This is our interaction temperature where the heat crosses the system boundary. And this integral is simply summing up the heat transfer over the temperature over the process. That's all it's doing. What if you have multiple heat transfers? We have Q coming in over here. We have Q coming in over here, or flowing out. You have all these interaction temperatures. T interaction, T interaction, all these interaction temperatures due to these various heat transfers. We've seen systems where there are multiple heat transfers, or certainly multiple heat transfers over time. So just in case there's more than one source of heat that we need to keep track of, I'm going to put a summation here. Why is a summation there? Because we may have multiple sources of heat flowing into or out of the system, okay? With that in mind, let us write the entropy balance in its full form and various versions. S balance, closed system. Let's make a little table here. You've seen this kind of stuff before. We have the basis, equation or expression. And then we have what? Units, S, I units, and English units. So, first of all, we have the entropy balance for an overall process. Overall process. That's going to be the equation we have written over there. Delta S from state 1 to state 2 is equal to the sum of the integral of del Q over the interaction temperature plus S gen from state 1 to state 2. Okay, that's a closed system entropy balance for an overall process. And we just discussed what these terms mean. Delta S is a change in entropy from state 1 to state 2. Del Q over T integrated, summed over all heat transfers. That's the entropy transfer due to heat flowing into the system. So heat brings entropy in or rejects entropy out of the system. And then we've got this S gen term. This is entropy generated within the system from state 1 to state 2 due to the presence of irreversibilities, okay? Now, what are the units on this? Well, the dimensions are, so we have the integral del Q over T. Del Q has units of energy and T has units of degrees. So the dimensions are energy per degree. So the SI unit would be what? A joule per Kelvin? Joule per degree Kelvin. Do not write joule per centigrade. Remember, all the second law stuff required temperature to be expressed in absolute terms. The temperature down there, the interaction temperature in the integral for the heat transfer, the transfer of entropy due to heat, that's got to be in absolute terms, okay? So a joule per Kelvin. English units, well, it can be a BTU per degree Rankine. That sounds good to me, per degree Rankine. And then we have the differential process, or infinitesimal. Differential process. So the delta becomes a D. ds is equal to the sum of del Q over the interaction temperature plus a little bit of S gen. Now I want to point out something here on the notation. There's a D here on the ds because S is a property. Entropy is a property. In fact, I'm going to write that right over here. Takeaway. Takeaways. S is a property. S is a property. So that's why it's got the D on here. S is a property or a point function. So the differential S is ds. The del Q, well, we already know that Q is a path function, so its differential transfer is del Q. We also know that S gen is path dependent. Why is it path dependent? Because S is positive for an irreversible process and 0 for a reversible process between the two same end states. So S gen is a path function. S gen is a path function, not a property, so it's got a del S gen there. Let's see, what about a rate-based? Rate-based. So I'm going to divide the differential process by dt, change in time, differential change in time, and I'm going to get a ds dt, which is S dot, if you like. I think I'll write that first. S dot ds dt is equal to sum over multiple heat transfers, Q dot over the interaction temperature. So I divided the del Q by a dt. Del Q over dt is Q dot, heat per unit time. And then del S gen over dt becomes a S dot generated, the rate of heat of entropy generated due to irreversibility within the system. Okay? Oh, I guess we need the units here. For the differential process, it's still energy. So joule per degree Kelvin, and then I have BTU per degree Rankine. The rate-based, it's going to be the same thing as the overall process or the differential, but divided by time. So a joule per second is a watt. So I have a watt per degree Kelvin, and if you like, a horsepower per degree Rankine, power or energy per unit time in English. I could also write the per unit mass overall process here, so everything would become a lowercase here on the overall process. So per unit mass, and I'll write overall. Everything's going to be lowercase here. So delta little s from 1 to 2, sum over all sources of heat, integral del little q over the interaction temperature, plus little s gen from 1 to 2. Okay? Everything becomes lowercase if it's on a per unit mass basis. 4 different versions of the entropy balance. What's another thing that we can spot here is kind of interesting about this entropy balance? One thing is we haven't seen work for a little while. We haven't seen any W's. We have the energy balance, we have Q and W are both on the left-hand side of the equation. So the energy balance said heat and work were sort of similar or equivalent as far as the energy balance was concerned. I don't see any W's or work interactions going on in these entropy balance. The entropy balance doesn't care about the work. It only cares about heat transfer and S gen. So what we can say here is Entropy is transferred by heat, but not by work. So heat transfers energy and, I guess I'll write and entropy. So heat transfers energy, Q, and entropy, S. But work does not. Work does not transfer entropy. Work does not transfer entropy. Okay, let's do a little problem here. Let's take a pause for a moment. We'll get it set up.